Okay, this is the last part of lecture 10. Let me first give the answer to that exercise we did, which basically asks you to express the transformation matrix lambda in terms of partial derivatives. Okay. So the first problem is we're working a spherical surface with radius r for a transformation from cylindrical coordinates rho and phi to polar coordinates theta and phi. Knowing the relation between the cylindrical radius uh, is and the polar angle is rho r, the radius of the sphere, sine theta. Okay, and using the fact that the transformation matrices can be written as partial derivative, I asked to find the transformation matrix. As I said, this is just a matter of substituting the partial derivatives. So the key point to understand XA is the so like 1, 1 is the x1 over the x prime 1. And x1 is rho, and x prime 1 is theta. So the first one is the rho d theta, and the lambda 1, 2 elements, the rho d phi, and so on and so forth. The rho d theta, of course, you just differentiate this expression rho with respect to theta, it's just r cosine theta. And d phi, of course, is 1. And the rho d phi and d phi d theta is all these are 0 because they are independent components. So here is the transformation matrix. Okay. And the feature I want you to know that this transformation matrix depends on theta, so therefore depends on position, which is not surprising because in a curved space, the base vector are necessarily position dependent. So therefore, the transformation would necessarily be position dependent. This is in contrast to a flat space. It is possible in flat space to have a position independent coordinate transformation. For example, Lorentz transformation example. This is from one coordinate to another way in a flat space. And I asked you to work out the transformation as partial derivatives. And then you find, in that case, called Lorentz transformation, only depends on relative velocity, which is a constant, and not depends on positions. And of course, the purpose of doing the second problem is also want to make sure to understand that the transformation written as partial has nothing to do with curved space. This relation is just chain rule differentiation, so it works for any coordinates, any situations. So the, the remaining item we need to discuss is so-called the Flatness theorem, in which we need to distinguish between how the description of a flat space versus a curved space. In a flat space, it is possible to find a coordinate system in which the metric is a constant. For example, the Cartesian coordinates in Euclidean space is just an identical matrix. Okay. For example, four dimension will be off a diagonal matrix that was 1, 1, 1, 1 on diagonal, off diagonal 0. For a Minkowski space, the metric will be also constant. In this case, the diagonal element is minus 1, 1, 1, 1, which is we call the eta matrix. Now, the fact that the metric is constant is only true in a flat space. In a curved space, it will be necessarily position dependent. But still, we can approximate the metric locally by a flat metric. Okay, and this is true for any dimensions, not particular for two dimensions, and this is called the Flatness theorem. Basically saying that you have a curved space in any dimension was described by coordinates x and a metric g, and at any given point p, which we choose to be the origin, you can always find a coordinate transformation from going x to x bar and g to go g bar, so that the metric is flat at p, meaning that the metric at this point p is origin, simple eta mu nu, plus a correction term. Now the correction term is second order, meaning because x deviate from origin is small. So this is a higher order term, more power x you have, x bar rather. Okay. So namely, as you can see, is a Taylor series expansion of the metric at the origin. There's the constant term plus a second order correction, meaning that the first order correction, which is the first derivative, vanishes. There's no first order corrections. The fact that the zeroth order can be chosen to be eta mu nu is not surprising because the metric at any point, the off diagonal represents the deviation from orthogonality of the base vector. So if you choose basis vectors which are orthogonal, and then you automatically get 0 for off diagonal elements. And for the diagonal element of metric, remember, is the length of the base vector. You can always normalize the length to be 1. Okay, and but of course up to a sign plus minus 1, and that's the signature. For example, the Euclidean space is 1 1 1 1, and for Minkowski is minus 1 1 1. That you cannot change by coordinate transformations. So up to correct signature, then you can always choose to be eta mu nu. The sort of main trivial part of the Flatness theorem is the absence of the first derivative term. Okay? In fact, you can always find a coordinate system so that the first derivative of the metric vanishes. Let's continue to talk about the Flatness theorem. So it's only in a flat manifold is possible to have a constant metric for the entire space. Okay. In a curved space, it's only possible to have a local Euclidean frame, like the X bar system we talked about in the last slide. So therefore, the message really the Flatness taught us is that the general space-time, the metric is characterized at a point not so much by its value, because we can always choose the value to be the flat space value, nor by its first derivative, because we can always pick a coordinate such that the first derivative vanishes. What really characterizes the space at this point is the second derivative, which it cannot be equal to 0, which characterizes the space. In fact, is what we later on call the curvature of the space. We'll talk about in this chapter 6 and in more detail in chapter 11, because the curvature is in some ways the more difficult part of the Riemannian geometry. We postponed it to the last chapter 11, which in some sense is the math appendix of the book. Anyway, the thing to remember, the second derivative of the metric represents in some sense the essence of the curved space. Okay? Because the zeroth order can be chosen and the first order can be vanishes. So it's the second derivative of the metric that's characterized the curved space. Now, takeaways from lecture 10. We talk about geometric description. We distinguish between so-called intrinsic versus extrinsic. The great lesson Gauss taught us that it's possible to make an intrinsic description. Means you can stay within the physics space. You never need to invoke any space outside the space you're interested in. You don't need embedding space. And you can choose so-called coordinate label points in the space by the Gaussian coordinates. Since the choice of Gaussian coordinates are arbitrary, so therefore you want the geometric relation to be unchanged, invariant under coordinate transformation, which in the curved space is position dependent. Because that, in fact, introduces some mathematical complications. The Riemannian geometry is a geometry fixed by length measurements, and the length is codified in the so-called metric tensor, which can be viewed as defined by this relation. ds squared is the length measurement is related to coordinate choices, the xa, xb, by the metric. And the metric itself can be determined by intrinsic length measurements, which we discuss in detail. Now, the fact you can have a constant metric only in a flat space, but in a curved space, you can have only a local Euclidean frame. So the space is locally flat because its metric is a constant up to a second order correction. Second order correction is turn out to be the curvature of the space.